Good morning, everyone. Thanks for joining in this lecture. Is there any question from the last lecture? Am I audible?
Yes, sir.
Yes, sir.
Is there any question from the last lecture? Okay. So let us start today's lecture. And today, so in the last lecture, what we did, we calculated the Fourier transforms of various signals, right? So in today's lecture, we will look at some properties of Fourier transforms. And these are the properties that we will study. So let us first start with conjugate symmetry. And I think we have already seen this for Fourier series also. So this property is if xt, signal xt is real, and x omega definitely is the Fourier transform of xt. Okay. So xt and x omega represents the Fourier transform pairs, right? So if you notice now from now onwards, I will use the symbol F to denote Fourier transform pairs. Okay. So x omega is the Fourier transform of xt and xt is the inverse Fourier transform of x omega. So if xt is real, x omega conjugate will be same as x of minus omega. Right? The similar thing happened in the case of Fourier series. If xt was real, then ak conjugate was same as a minus k. So the nature of properties will be same whether you are in the Fourier series or continuous time Fourier transform, discrete time Fourier transform, discrete time Fourier series, Laplace transform, Z transform. In all these transforms, the properties more or less remain same, and thus it is important that you do it for one case and then we can just relax ourselves for other cases as well. So let us see this again. Why is this? So x omega by definition is this. So x omega conjugate would be this, right? So if I take conjugate over this entire integration, you should know that conjugate of integration is same as integration of conjugate. Right? So we have to take conjugate over xt, but xt is real, so nothing changes there. But instead of e to the power minus j omega t, we will have e to the power j omega t. And by definition, this is same as x of minus omega. Right? If x omega you have defined like this, then this thing by definition will be x of minus omega. So if xt is real, x omega conjugate will be same as x minus omega. And what is the implication of this? If x omega conjugate is same as x of minus omega, what does it imply? It implies that mod of x omega is an even function. That is the first implication. Mod of x omega is an even function. And why is this? Because what is mod of x omega? Mod of, sorry. I'm sorry. So mod of x omega is same as mod of x omega conjugate, right? You know that the mod of a complex number or the conjugate of the complex number remains same. And mod of x omega is same as mod of x of minus omega. So what we get, mod of x omega is same as mod of x of minus omega. That means mod of x omega is an even function. Is it okay? Is it clear? Any doubt? No. And similarly, you can prove that angle of x omega, because x omega in general will be a complex quantity, right? In this case, it will definitely be a complex quantity because xt is real, right? So x omega is definitely going to be a complex quantity. So we can say that angle of x omega, if you have a complex quantity, you can define angle of that complex quantity as well, is an odd function. Okay. You can prove this also. I think it's quite simple. And some hint is also provided onto the slide. So moral of the story, the thing that I want you to learn and absorb this for the rest of the course is this thing. And you intuitively should understand that this thing implies that mod of x omega will be an even function and angle of x omega or phase of x omega, whatsoever you want to call this, is an odd function. Okay, so we are done with this. Some properties are simple and I will just skip it. For example, linearity. It's a very simple property. And linearity will be true for Fourier transforms, right? That's why we are studying the Fourier transforms for linear systems. So what does it say? It says that if xt has Fourier transform x omega, yt has Fourier transforms y omega, then a times xt plus b times yt will have Fourier transform a times x omega plus b times y omega. It should be definitely true and you can prove it, I think. There's no rocket science here. Okay. So I leave this to you to prove, though the proof, you can imagine the proof in your head. Let us look at the third property. Third property also we saw in the case of Fourier series. If xt has Fourier transform x omega, what is the Fourier transform of xt minus t naught? We have seen this in case of Fourier series, that when I shift a signal in time domain, what happens to its transform? The transform will shift or is getting multiplied by a phase quantity. So this thing is simply a phase. So x omega will be multiplied by e to the power minus j omega t naught. And can we prove this? Of course you can prove it. You simply, what should be the steps? You simply say that the Fourier transform of xt minus t naught is x omega tilde, right? So this should be this. Now what should I do? Change of variables. Is that what is expected? So I can say t minus t naught is lambda. So this limits, will it change? Probably not. So this is minus j omega lambda. I get confused. So t is lambda plus t naught. Yeah. So e to the power minus j omega t naught. dt is same as d lambda, right? So this thing is independent of lambda, can be pulled out. So what we have is this. And this by definition is x omega. And so x omega tilde is this thing. So this proves the property. Okay, it's very simple. So whatever I said, I also have written it, so you can go through it if you haven't understood what I said. Picture. This picture is important. What would happen to signal? This is important. This we have to keep in mind. Proofs are, I think, trivial. Now let us understand this slightly. What is the physical interpretation of time shift? Now suppose x omega is something like this. Let's say whatever. X omega, let's say something like this. Or let us draw mod of x omega, right? And let us say its phase of this is something like this. So when I shift this signal xt by t naught, this signal will have a different phase than this, right? This is the transform of xt. Now I'm looking at the transform of xt minus t naught. So what would happen is this phase is introduced. And what kind of phase is this? This is a linear phase. So if I, for example, plot this quantity, whatever is, let me call this as del phi. So if I plot del phi versus omega, you can see, so del phi is simply omega t naught, right? Del phi is simply omega t naught. So I can write this as e to the power minus j del phi, right? So I can write e to the power minus j omega t naught as this. You know that this is the phase, right? So let me call this phase as del phi, and del phi you can see is omega t naught. So when omega is 0, del phi is 0. And let us assume that actually the phase is not del phi, it's minus. I'm making so many mistakes. Let me remove this minus. Okay. So I can write this, I can think about this as e to the power j del phi. So del phi in this case is actually minus omega t naught. And minus, so let us assume t naught as some positive number. So the phase is something like this. So what you can say is this added phase is linear with respect to frequency. So it has a lot of implications, and that's why I'm stressing this. So suppose if you have a signal xt and if it has got certain phase, when you shift this signal with some t naught quantities, the added phase that this signal has will be linear in terms of frequencies. Okay, just one example. Suppose xt is something like this, sine omega t and sine 2 omega t. So it's a periodic signal. It's easy to think this in terms of if xt is sinusoids. If I shift xt by t naught, what would happen? You see that this phase will now become omega t naught. So if the sine has frequency omega, the added phase will be omega t naught. If sine has the frequency 2 omega, the added phase is 2 omega t naught. That means the added phase is a linear function of frequency. Okay. Suppose for some reasons, suppose xt is passing through a channel. Okay. Maybe LTI, may not be LTI. We do not worry about that. And what has happened is after passing through the channel, xt becomes something like this. So this component will become something like, what should I say? Omega T naught. And this component becomes also omega T naught. Okay, after passing through a system or through a channel or through whatever. So let me draw this. So there is a system, xt comes in and xt tilde comes out. And xt tilde comes out like this. What do we understand? This xt tilde is not the delayed version of xt, right? So xt tilde is not, you cannot write xt tilde as xt minus some t tilde, right? We cannot write it like this. Also, the meaning is that this sinusoid and this sinusoid are delayed. Phase changes also corresponds to the delay. They are delayed by different quantities. So the delay is not proportional or is not linear function of frequency. So they are delayed differently. So it is possible that these two components will arrive at the output at different time instances. Not in this case, but in other cases, particularly if we are looking at the pulse, which can be expressed at different sign components. And if these sign components are delayed differently, that means the phase change is not a linear function of the frequencies of different sinusoids. Then it is very much likely that these different sinusoids will arrive at the output at different time instances. Okay. So what will happen then? There is an effect known as dispersion. So what is dispersion? Dispersion, I explained, it's slightly not tricky, but if you think. So what is dispersion? Let us understand this. I think it is better by a curve. So suppose my xt is like this. Okay, a simple xt. Now you know by Fourier series, or even in the case, let us consider that this is a periodic to simplify because Fourier series are easier. So if xt is a periodic signal which has in one period something like this, that means it can be expressed in terms of sines. Okay, sines and cosines, I call everything as sines. So now if these sines, if I am shifting this xt by the entire xt by some constant t naught, then what will happen? Then all these sine phases will be proportional to the frequencies of the sines. Okay. That means there is no distortion at the output, just the output is delayed. Okay, but the output takes the same shape as the input, only that it is delayed. Now I am imagining the second situation in which different sine components, they go through non-linear phase change with respect to frequency. Then what would happen? Then at the output, you would not get xt minus t naught, but a distorted version of xt. And essentially it can be shown that xt gets broadened. So xt will get broadened if different signs of xt's go through non-linear phase change, because this situation will correspond to different signs arriving at the output at different time instances. So it will be leading to pulse broadening. Essentially, you can think it like this. Suppose you are having 5 friends. If you all take different travel routes to reach at a destination, and if you all 5 friends reach at different time instances, though you may have started together at the same point in time, what would happen? You will arrive at the destination at different time instances. So you can imagine a sort of dispersion there. In English also we can refer to that you have arrived in a dispersed way. That means you are arriving at different time instances. Okay, any question? Have I explained this enough?
Sir, like I have a doubt. Why will
Yeah.
it only disperse? Why will the purse only broaden? Why can't it shrink?
Why can't the pulse shrink?
Yes.
Yes, it's why can't see what non-linear phase change would do. So let us imagine a single thing, a single point. Okay. Now let us say that this single point, we are thinking this in terms of signs. If all signs go through linear phase change, linear with respect to frequency, okay, then what would happen? This point will be received as a point, but may be delayed. But now what is happening is a second situation can be that these signs are getting a non-linear phase changes. What would happen? Then these different signs will arrive at the output at different time instances. Okay, either you can arrive at the same time instance or at different time instances. There can be only two situations. If you arrive at the same time instance, then whatever you started with, you will get the same thing, but with a delay. The second situation is when you are arriving at different time instances. If you are arriving at different time instances, then what would happen? Then you are going to get broadened, right?
Yeah, but like different signals may overlap also, right? It's not that they will be independent. Like maybe signals at different time instant that started differently may come at the same point, may like appear at the same point when this distortion takes place. So why will it only broaden? That is like, my doubt.
So if it is easier to take an example and to understand this. So you are saying that yeah, how should I explain this? So let me take one simple example. Same situation happening in a physical medium. So suppose, so signal I am representing as a ray of light. Okay, one signal. Let us take it as an impulse. Okay, impulse is easiest. So I can transmit a signal in terms of ray of light. Single ray of light. Okay. Now what would happen? Let us say that we have a medium. One situation is I shine a ray of light and this ray of light arrives at the output just as a ray of light. Now the second situation is that this ray of light begins to take, because of different properties of the channel, different paths. So a part of the ray goes like this, a part of the ray travels like this, a part of the ray travels something like this, and you know that these different, if the propagation speed is same, but because they are taking different paths, they will arrive at different time instances. So an impulse which is transmitted through this medium, and if these different parts of this impulse energy is distributed, and if it begins to take different paths, what would happen? An impulse will get broadened. Okay, maybe something like this. So instead of impulse, because of this dispersive media, we have some other signal. Let me call this as YT. And YT is definitely larger than, or the width of YT is larger than that of the impulse. Okay. So now you know that XT can be thought in terms of impulses. Any signal can be thought in terms of impulses. But now because each impulse has got broadened, right? So if xt we are thinking as x tau delta t minus tau, or in discrete time also we can think. Now because each impulse has broadened, so this delta t has become some yt minus tau. So this is my resultant signal xt tilde. Okay. So basically what is, I can write this as, I'm running out of space. So xt convolution with delta t. And if delta t, because this is an impulse, right? If delta t is replaced by any other signal, yt. So xt convolution with yt. You already know that if yt is broader than delta t, so this convolution is always going to be broader than this convolution. Okay, or if you convolve two signals, right? So this is the convolution of these two signals. If you convolve these two signals, then it is always going to be broader than the signal with which you are convolving it. So xt convolution yt is always greater in width than xt. Okay, maybe slightly advanced at this stage, but this is actually that will happen in any practical system. If the proof is not probably very satisfactory, but I have tried to motivate through a physical channel and the physical reality. This is actually that will happen. If you shine a ray of light, the ray of light get broadens. And similarly, whatever input signal was, it will get broadened. For any more depth and to explain this more clearly, I also have to think about a mathematical model, which is not occurring to me at this moment. Okay, so I will think about it and probably try to give you a better feel if it is still not clear why there is only broadening and it's not shrinking. Okay, Avinav?
Yes, sir. It's like quite clear now.
Okay. Yeah, so this also I have an impulse gets broadened if there is different components of the impulse that is arriving at different time instances. Now let us look at this property. This is inverse of what we have studied. So we have seen xt has, if it has transform x omega, xt minus t naught, this we have just seen, has transform e to the power minus j omega t naught x omega. Here we are doing different thing. Here instead of, so here the x omega was multiplied by phasor. We are not doing that here. Here we are taking xt and multiplying this with the phasor. So xt e to the power j omega naught t will have this as the Fourier transform. Okay, and if you multiply xt with a complex exponential, this is known as modulation. You're modulating a signal. What is modulation? You take a signal and you multiply this with e to the power j omega naught t. The impact is that the transform will get shifted by omega naught. Again, proof is simple. So if we are looking at this signal, okay, and we are calculating the Fourier transform of this, saying this Fourier transform as x dash omega whatever, then you can see that this I can club this complex exponential with this complex exponential and I get this. And this by definition is simply x omega minus omega naught. So x dash omega is x omega minus omega naught. What do you think is the importance of this modulation? It's very commonly used in communication systems. And one very important modulation example that I can give is, you know that you can talk over telephones, landline telephones. Okay, landline telephones everyone might have used. And in landline telephone, what we use as a medium is a twisted pair. So the cable that connects to your landline telephone. And frequency response of a twisted pair, H omega, of a twisted pair looks something like this. So basically it goes from 1 megahertz to 20 megahertz. Okay. And let me make mod of H omega to be more correct. So the frequency response, let us assume, goes something like this, 1 megahertz to 20 megahertz. But the speed signal goes from 0 to 4 kilohertz. This is a hand drawn, so this might not be exact, but you can imagine that the speech signal varies from 0 to 4 kilohertz. And twisted pair goes from 1 megahertz to 20 megahertz. If I would have transmitted a speech signal over twisted pair, what should be the output?
Nothing, sir. Just zero.
Zero, right? Because H omega would give or make everything zero for 0 to 4 kilohertz. So how do we make the transmission? We make the transmission by shifting the spectrum of X omega to this band. And how do we do that? We simply take xt and multiply this with a complex sinusoid at 10 megahertz. So the speech signal after modulation is shifted to 10 megahertz to 10 megahertz plus 4 kilohertz. And now this signal is matched with the channel characteristics. So channel characteristics, you know, H omega will pass this. So modulation, the one main use case of modulation is to match the signal characteristics with the channel characteristics. Okay. Any doubt? So modulation and time shifting, they are somehow related. Yes, Shrimanti?
Sir, y of final y of omega would be x of omega multiplied with h of omega, right?
We haven't come to that yet. I will talk about it. We haven't said what is y of omega.
Okay.
But you are correct, yeah. So what is correct, and we will see this, y of omega, the output transform is input transform multiplied by frequency response. Y of omega is h of omega, x of omega. Correct. But we have to see this.
Sir, initially, how did you said that the response would be 0? Like if we don't know this?
Yeah, even if you don't know this, what you know is this. If you look at the signal, if you look at the signal, what is this x of omega? Let us make some notation. X of omega is xt e to the power minus j omega t dt. Now let us look at this equation. What do you think is x omega? What is this equation? It is doing the inner product, and I'm saying this with caution and some with some fear, because some of you can ask questions which may take to completely different domains. So I do not want to do this. But actually this is the inner product of xt with e to the power j omega t. Is this correct? Why I'm saying this with caution? We have seen the inner product. What is inner product? xt x1t conjugate dt integration minus infinity to plus infinity. Right? This is the inner product space.
Yes, sir.
So actually we are taking the inner product of xt with e to the power minus j omega t. Why I'm saying this with caution is because this is not energy signal. That is the problem. If you look at the energy of this is infinity. When I define the inner product space, I said that the two signals have to be energy signals. Okay. So, but you believe me that inner product, this is also a valid inner product operation because x omega is always bounded and so on and so forth. And you can also think about the inner product in case of these kind of signals. Okay, we should not get into more details about this because this will take us into functional analysis and things like that, which I want to avoid. But it is a good idea to start thinking about this. Actually, when we are taking the Fourier transform, we are taking a signal xt and we are taking the inner product of the signal xt with this. What does this mean? What does this mean? This means that this means so many things. This means that x omega is the projection of xt along this vector. Okay. X omega is the component of xt along this vector. Okay. This also means that when you have written this equation xt is 1 by 2 pi, this equation we have written. Okay. In this equation we have written what we are writing. So here we are constructing a signal xt, right? So this is the projection of xt along this. Okay. Now, so actually this is taking the dot product of a vector with a unit vector or with a vector. Here what we are doing is we are taking xt and we are writing this in terms of its projections. Okay, and how many bases we have? Uncountable. Because omega takes values from minus infinity to plus infinity, we have uncountable vectors. So if you look at this equation, it simply means that x omega is the component of xt along this vector. Okay. Now I look at h omega. I look at h omega. H omega is what? H omega is component of ht along this vector. Okay. The same equation. Now you know the forces and all these things. Suppose I have a force applied on a mass. And let me take a force like this. So if I apply a force on a mass like this, you know that the force can be decomposed into these two terms if you want. So acceleration in this direction depends on the force in this direction, and acceleration in this direction depends on the force in this direction. That means output ay depends upon fy only. It has nothing to do with f of x. Similarly, the output in this direction, in the direction of e to the power minus j omega t. Okay, output in the direction of e to the power minus j omega t should depend only on x omega and h omega. Okay. So by just looking at these two equations, can I not say y of omega, which is the output in this axis, is simply, without using any maths, is simply x omega times h omega. All right, so this is giving you some more flavor, and I will I will talk about this for a few more minutes. So let us see what I have said. I have said that the projection of the input on this vector is x omega. That means this is the component of xt along this direction. This is the response of the system. Response. Okay, how system responds in this direction. So the output should be the response of the system in that direction, right, in this direction, multiplied by the input in this direction. Okay. So even without using any maths or whatsoever, I haven't used any maths, I just have used the vector analysis. I can say y omega is x omega times h omega. Any question on this part?
So won't this be true like only in the case when h omega for different omega are orthogonal?
This will be true when e to the power minus j omega t is orthogonal. Yeah.
Okay, that is obviously fine.
And we have already shown this indirectly. We have shown that this equation, I think in the last lecture, e to the power minus j omega t, whatever, d omega is 2 pi delta t. Or I think we have said for delta t. Okay.
Yeah, okay, fine.
So now you look at this equation telling me something very important. Or let me just say omega 1 minus omega 2. Omega 1 minus omega 2. That means if omega 1 is different from omega 2, I get 0. If omega 1 is same as omega 2, I get something. So anyway, it's orthogonal. Okay. So this equation that we have proven in the last lecture is giving me a lot of insight. This is also telling me, which is otherwise a horrendous thing to prove, that these complex exponentials, I know that these complex exponentials, if we take in a period, let's say in some period t, we know that they are orthogonal, right? If this omega is 2 pi by t and so on and so forth, we have seen this in Fourier series. It was very easy to prove. Anyone can prove it. But now here we are saying these complex exponentials are, even though this omega is like a continuous variable, even these complex exponentials are orthogonal to each other if omega is choose it differently from any other omega. And this is the proof. Any other thing?
Sir, like you said that x omega is expressed as like a projection of xt in the direction of e to power minus j omega t, and we take the summation over t. So it is essentially the sum of different vectors in different directions. But then how did we like conclude from that the x omega, what the direction it infers in, and the product of h omega will give y omega? As in, even if omega is same, t will differ, right? So if t changes, the direction of the vector also changes.
No. No. So let me say it again. Maybe you have not heard me correctly. So let us look at this equation again. What is this x of omega? X of omega is the projection of xt. Okay, xt is a signal, time domain signal. Fine.
Yes, sir.
In this direction. Okay, e to the power minus j omega t. But x omega itself is not a function of t. It is simply the projection of xt along this. So if I make a picture, so I have xt, some xt. Okay. Now if I ask you, let me just concentrate this vector. This a single vector, because all these are orthogonal vectors. So I'm just willing to look into one direction, in this direction. If I ask you what is the component of xt along this direction, you will tell me x omega. So when I am looking at x omega, I do not have to look at any other part of xt because it's not required, right? So the same example, you have a force. And if you're looking in this direction only, you do not want to know what is the force in this direction. It's irrelevant. So when you have chosen this direction, you only look at what is it in this direction. So xt had components, many components, but let me choose this basis. And I ask you what is the component of xt in this direction, you will tell me x omega. Okay, then I forget about anything else. Now I ask you h omega, then I ask you what is the response of the system? What is the response of the system in this direction? You will tell me h omega. Okay. Then I tell you, okay, then the output should be what? Output y of omega should be what? Output, what is y of omega? This is the output in this direction. So the output in this direction, y of omega, should be the input in this direction multiplied by the response of the system in this direction. Right?
Yes, sir. Now it's clear.
Any other question? Okay. So this viewpoint, I don't know if any one of you have thought to answer this, but this is an important viewpoint because this allows us two things. First, it allows us to prove convolution very intuitively. I have not used any maths. We will do maths also in this lecture, but here I am not doing any maths and still I have derived at this beautiful equation. So this gives me some physical meaning of this. What is the physical meaning of y omega is same as x omega times h omega? Okay, so it's very important thing to remember. Now, still it didn't answer because this is what I had in my mind when I have said that the output should be 0 because h omega, or the response of the system to these set of frequencies, is 0. That means in the output, these set of frequencies, whatever. So here if you see that you have frequencies only below 1 megahertz. And if the response of the system is such that it makes everything 0 below 1 megahertz, then you know that there will be no signal in the output domain. Maybe we are using some indirectly some information about this. Okay. You are already thinking in mind this, and possibly I should have introduced this property before. But anyway, if you know this property, then you know this. Okay. Maybe I should change the order of these slides. All right. So this is what? Convolution. Yes. Modulation is okay. Physical understanding of modulation is okay. Also, we have looked at the vector picture of Fourier transforms. Convolution. If xt has Fourier transform x omega, yt has Fourier transform y omega, xt convolution yt will have Fourier transform x omega, y omega. And this is exactly right, because you give xt to a system LTI, output yt is ht convolution with xt. And its Fourier transform y omega is h omega x omega. Okay, so we know that this indirectly should be true, but this is something which may not be even valid for non-LTI systems. So this property is true in general. If you have two signals, the convolution of these two signals in time domains, Fourier transform is the multiplication of individual Fourier transforms. So let us look at this. So what we are doing is some maths, because this is slightly tricky. We have to calculate Fourier transform of xt convolution yt. This. And xt convolution yt is this. Right? Now its Fourier transform. So this is xt convolution yt is e to the power minus j omega t dt. Okay. Now again the change of variables, integrations, whatsoever. You are free to do all of this in this course, no problems. So what I do is I put the tau here, x tau I push here, and I look at this signal. So this part, then this part, and this part. Okay. What is this? I need to do some change in variables. So t minus tau, let me put as lambda. I may have done this. So let me put t minus tau as lambda in this equation. So this equation simply becomes y of lambda, t minus tau is lambda, and you will get two terms here. And again, this term is not a function of lambda, can be put outside this integration. So I'm putting it here. And so this term, if you see, is simply what? Y of omega. Again, this is not a function of tau, so this could be pulled out. So what I remain is this thing, and this by definition is x of omega. So Fourier transform of xt convolution yt is this. Any doubt? Okay, fine. So let us understand this importance. For LTI system, I already know that yt is xt convolution with ht, right? Ht is the impulse response of the system. So in frequency domain, we can write this equation. Y omega is x omega multiplied by h of omega. Deriving this, I haven't used any vector knowledge. Okay. So similar results can be derived otherwise also. Now, if I look at this equation, I can say several things. First thing that I can say by looking at this equation is it's simpler equation than this, right? Because suppose You know input signal xt. Suppose you know impulse response. What should we do? We should calculate the convolution. Convolution is a complicated operation. In signal processing also, convolution is a very difficult operation to compute. Why is it a difficult operation to compute? Because the whole of xt, so if this is xt and this is the impulse response, the whole of xt has to be multiplied with whole of ht, not multiplied but convolved. So convolution involved the whole of x and of whole of h, and then there is some operation on x and h, and then you finally get some answers. So it's a complicated operation. On the other hand, once you have found the frequency response h of omega, whatever input you have, if you quickly calculate its Fourier transform, you can quickly calculate y of omega because it's a multiplication, point to point multiply. Multiplications are easier operations. So you take x of omega, you simply have to multiply h of omega. You get y of omega and take its inverse Fourier transform. Taking Fourier transforms is easier. Multiplication is easier. Taking inverse Fourier transform is also easier, rather than doing the convolution. Okay, so from the complexity point of view, first of all, doing this thing is important. It's easier. The second thing is important thing here. The entire signal xt, the entire, even this part lying close to infinity, has to be operated with every part here. Even this signal has some effect when it gets multiplied here and so on and so forth. So every part of the signal. So if you're computing, let's say output here, yt, okay, at this point. Now this point is not influenced by this and this, but maybe something which is very far in infinity, something which is very far here, something which is very far here, right? So this part is influenced by a lot of things in this convolution. But look at this equation. Point-wise decoupling. You have x of omega, you have h of omega. So to get y of omega, you have to simply multiply this part with this part. Easy. So it provides us point-wise decoupling. And point-wise decoupling is also very intuitive, right? It shouldn't have taken any maths. This is the output in the direction of e to the power minus j omega t, input in the direction of e to the power minus j omega t, response of the system into the direction of e to the power minus j omega t. Very easy to understand this point-wise decoupling. The last thing by which it is important, so I have said computationally efficient, point-wise decoupling, this thing. It proves a point that linear time invariant system cannot generate new frequencies. Why? Because suppose x omega is like this. So that means this is 0, this is 0. Whatever might be your h omega, whatever, does not depend. Your y omega, you can say with certainty, should be 0 here for this part. Rest you may not say, but you can simply say because y of omega is x omega h omega multiplied. So if x omega is 0 in this part, your y omega should also be 0 in this part. Similarly, if your x omega is 0 in this part, your y of omega should also be 0 in this part. That means if certain frequency is not present in the input, right, that frequency will also not be present in the output. So meaning is linear time invariant system cannot generate any new frequencies. Any question? No, yes, two answers. Any question?
No, sir.
No, sir.
No, sir.
Okay, good. Now let us look at some other properties. Maybe I will take 5 minutes of break. Okay. We will resume at 11, not 5. Okay, so I am back. Just to answer one question back, this dispersion one. You see, I have already proven now. This is for a periodic signal, but you can also show that for aperiodic signals, that these sinusoids, okay, will be orthogonal, right? If they are orthogonal, they cannot cancel each other. Okay, Avinav? So similarly, if you have a aperiodic signal, these complex exponentials are orthogonal. That means they cannot cancel each other. So they can only spread the signal. Okay, just one small point. It just occurred to me, and I think that's it, to prove that there will be only pulse broadening and no shrinking. Okay, now come back.
So can you repeat once? What did you say?
So Avinav's question was, why can't these different sinusoids cancel each other after getting a nonlinear delay, right?
So I did not ask about canceling. I said, why can't they overlap? Like even overlapping will cause it to shrink, right?
No,
It may not
overlap.
cancel, but
Yeah, overlap also, if they have to overlap, there has to be non-orthogonal, right?
yeah, that is fine.
Yeah. So what he said was, if this is shifted by some omega t naught and this is also omega t naught, then there might be a possibility that this overlaps with this. But actually these components are orthogonal to each other, so no overlapping or cancelling is possible. Similarly, you can extend the same thing for aperiodic signals where these are the bases. And again, you can think that this is orthogonal to any other frequency, right? So they cannot overlap or cancel each other.
Okay, sir.
So where I was, yeah, duality. So xt has a transform x omega. Then this xt, so this is x omega, this is xt. It will have Fourier transform 2 pi x of minus omega. So important thing is that this comes in here and this comes in here. That means in simple terms, and I say this a very easy sentence so that it remains in your head forever. If table has a transform which is chair, chair should have a transform which is table. Okay, so that it stays. And how do we prove this? Proof is very simple. Xt we know is given by this equation. Then we just do change in variables. So instead of t, we simply change t to minus omega. Okay, I can do that. And this becomes this. And this, you know, is nothing but it is the Fourier transform of xt. Okay, this side. And the Fourier transform of xt will be 2 pi x of minus omega. This is what we have to prove. Okay. Fine.
Yes, sir.
One important point. Is there a duality in Fourier series? Continuous time Fourier series. Did we study it there? Why not?
Sure. Because like Fourier series might not be periodic, right? Even if the function is periodic.
Exactly. You cannot talk. So you look at these two signals. Xt and x omega, they are same. Xt is a continuous time signal, aperiodic. X omega is a continuous frequency signal, aperiodic in general. So duality makes sense in these two kinds of spaces which are similar. In Fourier series, we had periodic signal on the one hand, periodic, continuous time, and a series, A case, is a discrete, aperiodic. So there is no sense in using duality here. Duality will not make sense, of course not. Okay. So in future, maybe we will look at the transform of discrete aperiodic signal. So this is continuous time Fourier series. In future, we will look at the transform of discrete aperiodic signal. And discrete aperiodic signal transform will be what? Periodic. And continuous frequency. So what do we see? There is duality across transforms. Okay, we will look at this in future when we do this, but right now in CTFS, in continuous time Fourier series, because the nature of the transform is different from the nature of the signal, there is no duality. But because in CTFT the nature of the transform signal is the same as the nature of the signal, and thus we can talk about the duality. Keep in mind. Now using duality, this is what you have to prove. We have already seen that xt convolution yt has the transformed x omega y omega, and similarly using this fact and using duality, you can prove that x omega convolution y omega. So if I convolve to frequency domain signal, what should be the answer? Answer will be multiplication in time domain, right? Because convolution in time domain leads to multiplication in frequency domain. Convolution in frequency domain should lead to multiplication in frequency domain. So this is what would happen. Okay, and there is factor of 2 pi also. Okay, so if you forget these constants, it's perfectly fine. Everyone does it. These constants are not so important. The message is important. The message is as following: convolution in time domain, multiplication in frequency domain. Convolution in frequency domain, multiplication in time domain. Okay, you can prove it using the duality principle. So go ahead and prove it. Now another important concept. Parseval's theorem. If xt has transform x omega, yt has transform y of omega, then this Fourier transform is a unitary transform. What I mean by unitary transform? Have you seen unitary transform in matrices, algebra? So for
No,
every
sir.
question, two answers, yes or no? No.
No, sir.
So unitary transform is the transform which preserves inner products. Okay. So inner product of the time domain signal, this is the inner product, is same as the inner product of the frequency domain signal. Of course, with some constants. Constants are irrelevant. Okay. So inner product of the time domain signal is same as the inner product of the frequency domain signal with some constant, and this is known as Parseval's theorem. It's an important theorem. Let us try to prove this. Okay. And because it, yeah.
So what do we mean by preserves inner product?
It simply means that this inner product, so here we are taking the inner product of the time domain signal. Whatever you get, some number, let's say some number you get a, you might get a complex number. And if you have taken the inner product of the transforms of these two signals, you will simply get 2 pi a. Okay. So you will get the same inner product, whether you do the inner product in time domain or in frequency domain. You will get the same inner product with some constant. So 2 pi is multiplied, but that's it. So in time domain,
definition remains same, right?
Sorry?
That inner product definition remains same. Is
yes,
that what it means?
Yeah, and the inner product of two time domain signal will give you the same answer as the inner product in frequency domain signal. except for a trivial constant. So, okay, so yeah, we have to prove it. We haven't proved it yet. So let us look at the proof. Where is the proof? I guess this is the proof. This should be the proof. So YT conjugate. So YT has a Fourier transform Y omega. We know already conjugate symmetry. YT conjugate should have the Fourier transform Y omega conjugate minus. Have we done this property? No, I don't think so. But we have done this in Fourier series, so you can do this yourself, right? So just remember, if YT has this transform, YT conjugate will have this transform, Y conjugate minus omega. And this property we already know from multiplication, right? The multiplication of two time domain signal Fourier transform is this. Using these two things, we can prove the Parseval's theorem. So if I look at, I should write it here, XTYT Fourier transform e to the power minus j omega t dt. Okay, let me write this in full. Minus infinity to plus infinity. So this we know is same as 1 by 2 pi x capital x lambda y omega minus, what should I do? Let me write small. Let me start from here. XTYT e to the power minus j omega t dt. This is same as 1 by 2 pi x lambda y omega minus lambda d lambda, right? Using this property. Now, instead of YT, I have YT conjugate. So instead of y omega minus lambda, what should I have? I should have y lambda minus omega, because this minus y lambda minus omega conjugate. Okay. And now I can put omega as 0. Simplest. Omega is 0, I can put. So I get XTYT conjugate dt is simply 1 by 2 pi minus infinity to infinity x of lambda y of lambda conjugate d lambda. So I have proven Parseval's theorem. Okay, I think it's simple. This is what is proven here. Parseval's theorem has been proven using these two steps. Okay, so now we can make some changes also. I can put YT as XT. So I will get XT conjugate. And here I will get x lambda conjugate. And this quantity is nothing but this. Okay, and this is simply this. And so this is the energy of the signal, right? We have seen this is the energy of the signal. And so you can also calculate the energy by using the transform domain signal. Okay. And because the total thing, this is energy, what should be this quantity? This is energy divided by time, right? So this is energy time density. Similarly, the total thing is energy. So what is this quantity? Energy spectral density. Okay. So the moral of the story is you can calculate the energy of a signal in time domain. You can calculate the energy of the signal in in Fourier domain. Okay, and the energy is same, just the difference is in one constant. Any doubt? No. Okay. So if I look at Parseval's theorem, I have said that the inner product is independent here. It's independent of the choice of unit vectors, right? The unit vectors in this case, what are the unit vectors, by the way? When I'm writing xt yt conjugate, where are the unit vectors here? What are the unit vectors? Recall that the unit vectors here are impulse functions. Okay, think about this. And here you can also calculate inner product by this, and the unit vectors in this case are complex exponentials. So inner product is independent of the choice of unit vectors. It's a unitary transform. Inner product remains same, whether you do this on the original signal or on the transformed signal. Last two properties and then we are done. And these are rather easy properties. If xt has a transform x omega, dxt by dt has transform j omega x omega. Similar result as in Fourier series. Okay, the proof is also simple. You start with this signal, you differentiate this, and on differentiation you have j omega x omega. Okay. So just one small point here. Suppose you have xt input and you give to differentiator, your output is dxt by dt, right? Xt has a transform x omega. You know dxt by dt has transform j omega x omega. And this is a LTI system. So what is the frequency response of a differentiator? J omega, right? Frequency response of a differentiator is a j omega. So if I plot mod of j omega, mod of h omega, sorry, this will be a line. Okay, I'm plotting mod of h omega, so you will have something like this. Now, what kind of filter is this? What kind of filter is a differentiator? Low pass, high pass, band pass, all pass, band stop.
High pass.
It's a high pass filter. Okay. And you can look at, suppose if we take a signal like this, on differentiation we get these frequencies, this signal. And I have already said that the edges, these things, they correspond to high frequencies because high frequencies are only coming out. Okay, so whatever is of high frequencies is coming out and this part has disappeared. Any question?
So can you explain this diagram? High frequency are present in the edges.
So if I differentiate this signal xt, what should I get?
Yeah, after differentiation I get it. We get this, but analytically, why should high frequency be present in edges?
Because if you look at differentiation response, and if you see that you get this, why do you get this? Because of these edges, right? You get this output because of these edges. And differentiation allows only high frequencies to pass through. Right? So this part has disappeared. So this part is not present in differentiation. So this part should correspond to low frequency. Okay, some intuition. And this part is coming out. So only two things are coming out, right? This part has disappeared, and then there are things corresponding to these things which are coming out. That means this part should be belonging to high frequency and this part must be belonging to low frequencies. Okay.
Yes, I got it.
Any other question? Integration. If xt has transform x omega, what is the transform of this signal? Running integration of xt. No problem. How do we think about this? The easiest thing to think about this without any fuss is this thing is same as convolution of xt with unit step. Right? If I convolve, then I get this, right? And the tau has to be less than t for this to be 1. So tau has to be less than t. So we get this. So this is running integration. I should have been careful with my notation. So this should be x of tau, d tau. Okay, so you already know this. Xt has a transform x omega and ut has a transform, everyone, 1 by j omega plus pi delta omega. And convolution leads to multiplication. So the transform of this signal should be this multiplied by this, which is this part. And when x omega multiplies by pi delta omega, we only get pi x0 del omega. This part. Okay. Any question? Okay, so we have finished with the properties of Fourier transforms. But the story doesn't end here. You have to give me 5 minutes more because I want to touch upon another important topic, which is differential equations. Just 5 minutes. I won't take much time.
Sir, I was wondering out.
Yeah.
Sir, the h omega for integration, integrator or accumulator would be the same as for ut, right?
Yes. H omega for integrator is same as u omega. Yeah.
Yeah, okay.
Okay. So this topic is slightly tricky because this is not well explained in Oppenheim and I feel that there are some errors. So you have to pay attention to this. So far we have seen the basic CT system is something like this, right? Built using integrators and multipliers and errors. Okay. This CT system, what you have is definitely what? It's a linear time invariant. Everyone should agree. And this system is also causal. So it's a linear time invariant system and a causal system. If you can represent a linear time invariant and causal system by this kind of block diagrammatic representation where there are three kinds of components, multiplier, integrators, and adders, then of course you can represent this system also in terms of linear, constant, coefficient differential equations. Okay, what are linear, constant, coefficient? These coefficients are constant, they are not function of time, and it's a linear because the derivatives of output is same as sum of derivatives of input. So sum of derivatives of output is same as sum of derivatives of inputs. So it's a linear. So again, I repeat, if you have an LTI and causal system, causal is also important. This is missing in Oppenheim. If you have linear time invariant and causal system, and if you can represent this in terms of this kind of structure built using multipliers, integrators, and adders, then you can express this in linear constant coefficient differential equation. Remember that if you have a linear constant coefficient differential equation, if you have, this may not be for LTI systems. So if you have linear constant coefficient differential equation, this may not be for LTI systems. For example, this system is not linear time invariant. We have seen this already. But this will have a linear constant coefficient differential equation. So having linear constant coefficient differential equation does not imply that this is for an LTI system. Other way around is also not possible. LTI system may not have a linear constant coefficient differential equation. For example, this kind of a system does not have a linear constant coefficient differential equation. Okay, so only LTI and causal systems which can be expressed or which can be built using these three components. And this is usually everything that we do in engineering. We do not worry about those systems which cannot be built like this, because anyway you have to build systems, right? Otherwise, why we are studying them? So if we are building systems, we will use only these three things. If you can build a system, then you will have a linear constant coefficient differential equation. Okay. So if you have a linear constant coefficient differential equation for an LTI and causal system, now one more catch. If the system is also stable, this is important. Why is this important? If a system is unstable, then it will not have h of omega. Right? We know that for sure a system will have a frequency response only if it is stable. If the system is unstable, it will not have a frequency response. Okay, so this is also an important addition. So LTI, causal, stable. Now we are good to go. Then if you have to solve this differential equation, you can use Fourier transforms. Okay. So Fourier transforms can only be used if the system is linear time invariant, if the system is causal, if the system is stable. Okay. Then I know that this part, kth derivative of yt. What is this? This is simply j omega times k, right? Differentiation produces one differentiation produces j omega. So kth differential derivatives will produce j omega times k, y omega. And similarly, you can write it like this. Now, if you have this equation, now this y omega and this x omega is not a function of k. So we can pull this out. So frequency response is simply y omega by x of omega. Okay. Okay. Frequency response is what? Y omega by x of omega. Always. Is frequency response always y omega by x of omega, or there's some catch?
So it should satisfy these three conditions.
No, 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 no. No, not at all. I think you're. If the system is linear time invariant, then it will only have h of omega. But causality is not required. Okay. Causality is only required if you want to express that LTI system in terms of differential equations. Okay. So I'm asking you a different question. If you are having linear time invariant, causal and stable system, then so if you have linear time invariant and causal, then this thing makes sense. If you have linear time invariant, causal and stable, then this thing makes sense. But when I am writing h of omega as y of omega by x of omega, you have to remember one thing. Suppose my x of omega is something like this. So it's 0. Now when this is in denominator, what does it give me? Infinity, right? Okay. So when you write, suppose x of omega is given to you. X of omega is given to you and y of omega is given to us. Okay. Suppose we want to find out h of omega from y of omega and x of omega, you might run into trouble. Okay. So these types of inputs will not allow you to compute, though this is always correct. This is always correct, always true. There is no ambiguity about this. This is always true. No ambiguity. But suppose you are given in questions y of omega and x of omega, and x of omega is like this, then we'll run into trouble. Okay, so just keep in mind. Okay, but this equation is always true. So if I have to find y of omega, h of omega like this, what should it be? This should be this thing divided by this thing. Okay. It's easier to solve this with an example. Suppose I have this differential equation to solve. And we are given that LTI system, causal system, stable system, so on and so forth. So h of omega is this thing, right? This by this. So B case corresponds to the derivatives of inputs. Okay. So here, look at this. I think it will be easier. So xt, no derivative, and its coefficient is 1 j omega raised to power 0. Then this signal has constant 1 because this is one derivative, j omega to the power 1. Okay. And this signal similarly 6 corresponds to this, 5 corresponds to this, 1 corresponds to this. So we can now find h of omega like this. If you can find h of omega like this, you can use partial fractions. And using partial fractions, I can write it like this. Once I have written it like this, I can find out impulse response by inverting these two different parts. And I can do this. So the inverse of 1 upon 2 plus j omega is what? E to the power minus 2 tut. Okay. And inverse of this part is e to the power minus 3 tut. So with this approach, you can find the impulse response if the differential equation is given for linear time invariant, causal and stable system.
So can you go to the previous slide once?
More?
Yes, sir. So where you said the xt, which x of omega, it could not be calculated. Like if it was completely 0, then we could not do. But some coefficients we can get, right?
Some coefficients, but not in entirety, right?
Yes, others would be 0. So
no, others may not be 0 because x omega is 0. So this is y omega by, let's say, for omega tilde. So h omega tilde. So this is 0. If x omega tilde is 0, you will get y omega tilde by 0, which is undefined.
Okay. I mean, then we need to have some value for all values of omega, right?
Yeah, so you need to have x omega, which is non-zero for all values of omega.
Okay.
And what is that x omega? What is the nice x omega that you want to have? Nice x omega. Constant.
10, yeah.
Right? If you have constant x omega, then there is no trouble. Y omega is simply h of omega. So if x omega is constant, what is xt? Impulse. That's why we learn the impulse response. Okay. Why do we learn impulse response? Because impulse excites all frequencies. That's why impulse response is the complete characteristic of an LTI system. Because if you look at the transform of an impulse, it's a constant. That means it is exciting all the frequencies. Okay. Whatever output you get or the impulse response does is the complete characteristic of an LTI system. You can also think it in this way. Okay. So try to take inputs. Right? If you are doing it in lab, if you are calculating x omega, you would know that x omega being constant is the best thing. And that in essence will correspond to taking an impulse as an input. Any other question? Then we stop this lecture now. Sorry for making it longer.
So one thing, so in the quiz which we have, the offline quiz, will we have the syllabus of the minor also?
I haven't thought about it. Basically not. I think in quiz we should focus on what we are covering after minor.
Okay. And so will it be objective or like minor?
It will be like objective. Pattern of the quiz will be same. Just now we will grade it because I see all the students before my eyes attempting it. So I think it's fair for everyone.
Yeah.
Any other thing? Of course, I will give you some subjective questions to solve. But that is if you want to solve it at your home or hostel or wherever. Okay, so you have enough practice because major will be subjective.
And so major would be like on Moodle, or we'll have to submit?
No, Moodle will major will be typical exam. Okay, so pen and paper exam. No Moodle is involved here. Okay, any other question? No, thank you so much for attending this lecture. See you next time. Bye.
Thank you, sir.
Thank you.
Thanks.